Yeah, so hello everyone. Welcome to the Topology Optimization webinar. Today is our 22nd session. It is kindly organized by Professor Gilho Yoon from Hanyang University in South Korea. Thank you for organizing this session, Gilho. Please take it over.
Thank you, everybody, and it's really nice for the organizing this talk webinar. And due to the time differences, and some people are very should wake up earlier, and so thank you very much for joining the all of them. So we have the 5 speakers, and each speaker has 15 minutes, 12 minutes for the presentation, and the 3 minutes for the discussion and the Q&A. So the first speaker is Alberto Donoso from Spain. So can you start now, Alberto?
Okay.
Yeah.
Okay. Hello, everyone. Thank you very much, Gilho, for the presentation and also for the invitation to this webinar. It's a pleasure for me to share this work with all of us. Well, this work has been done in collaboration with my colleagues Ernesto and David, and it is about how to avoid the formation of holes in topology optimization using graph theory. So to start with, let me tell you how we got that idea from graphs. Okay, well, a graph is basically a set of vertices, also called nodes or points, and they may be objects, people, computers, or whatever, which are connected by edges, also called here links or lines. And well, basically a graph represents some kind of relation among those nodes. Nowadays, we can find graphs everywhere, and in particular, the typical regular mesh that we use to solve topology optimization problem is an example of a graph. Sorry. Here we will focus on undirected simple graphs, which mean that edges link to vertices symmetrically with no orientations. Yeah, associated with to a graph, we could define different matrices, and here we pay attention to the Laplacian matrix that somehow remind us the topology of the stiffness matrix in topology optimization problem. Is built in a very easy way, and I will try to explain you briefly. If we match the columns of the matrix with the nodes in the graph, and we take a look to the first row, this number 2 means that we have 2 connections, node number 5 and node number 2 with node number 1. The second and the 5th entries are -1s because an edge leads from node number 1 to node number 2 and node number 5. And the rest of entries are null because there are no connections between node number 1 and node number 3, 4, and 6, and so on. Well, this matrix has really important properties, and the more relevant are the following. It's symmetric, it's posit semi-definite, and the sum of components of any row is 0, so that means that the first eigenvalues equal 0. Well, there is a classical result in graph theory that connects this matrix with an important concept, which is graph connectivity. And this result says that the second smallest eigenvalue of this matrix, which is called algebraic connectivity, gives us a measure of how well connected a graph is. So in other words, it means that the number of times 0 appears as an eigenvalue in the matrix coincides with the number of connected components in the graph. So as a consequence, we could state that the second eigenvalue is non-negative if and only if the graph is connected. Well, we can extend this result to weighted graphs. That is, graphs that on every edge we have an associated value, a weight, that may take arbitrary values and that tell us how strong the connectivity is between two nodes. Remember that whereas in simple graphs, all the connections are equally important whenever they exist, which means that the weight is equals 1, and h's with weight 0 are omitted. Here, these weights may take arbitrary values. And using the same procedure as before, we can build the weighted Laplacian matrix. So the question now is, how can we use those ideas in topology optimization? Well, we can use these ideas to characterize the connectivity in binary finite structures like the following 4x4, where black means solid and void and white means void. Regarding the centroid of void elements, as a node of a particular graph, we have the following graph representation. That is, we have two isolated graphs. Well, if we compute now the first eigenvalues of the Laplacian matrix associated to these two graphs, we have the following. The first eigenvalue and the second are null because we have two connected or two isolated graphs associated to the void phase, but not the third one. So we can state that if a structure has an enclosed hole, the void phase is not connected. The void phase is not connected, but unfortunately, that also happens in a situation like this one and in this new one, because here we have three isolated void regions, which means that the third eigenvalue associated to void is equal 0. But if we consider an extension of the design domain, for instance, an outside void frame of few elements, then we observe that the second eigenvalue of the void is greater than 0. So we can state that the number of inner holes in a structure is the number of connected components minus 1 of the void phase in the extended domain. Now we need to integrate the solid phase in the problem in order to model not only the connection void-void, but also the connections between void and solid elements. Think that a solid element in our problem implies a null row and a null column in the matrix, in the Laplacian matrix, that increase in 1 unit the multiplicity of the 0 eigenvalue. And I would say that it does it in a wrong way. So we can say that as two void adjacent elements are connected whenever its product of void density are close to 1, we propose here to define the weights for the graph in the following way. The weights are the product of its void densities powered to an exponent q, and we also need to introduce another parameter as the SIN method does. So the aim of the first parameter, the n of q, is to weaken the possible connections in the structure, and W-min is necessary to guarantee coercivity in the problem, and also to avoid the singularities I have mentioned before. All this leads to solve the following eigen problem that has been previously shifted to avoid the 0 eigenvalue. And even though this is not mandatory here, I think it's convenient, as we will discuss later. Okay, so to see how our approach works, let's consider two optimized structures. The picture on the left with some gray areas, and the picture on the right, black and white. When computing the first four eigenvalues, we observe the following. The first eigenvalue is always 1. Remember, we use shifting. And the second and the third eigenvalues are almost 1, but they are not 1 because of the W-min parameter. And the fourth eigenvalue is greater than 1. We also observe that the higher the power q, the lower the fourth eigenvalue, but it doesn't really mind for our interest so far. The important thing is that we have 3 isolated void regions, and its number coincides with the multiplicity of the unit eigenvalue, which is also 3. In the other example, we have included an upside void frame to see this effect in the method, and the new results are coherent with this new situation, because now we have just two void regions, two connected void regions, and it coincides with the multiplicity of the unit eigenvalue, that in that case is 2, because two eigenvalues are close to 1. So we could say that our method detects successfully how many disconnected void areas are, because it coincides with the multiplicity of the unit eigenvalue. So the question is how that we could incorporate this idea in a topology optimization problem to avoid the formation of holes. Well, we just have to impose that the second eigenvalue be positive, be greater than 1, in case we use shifting, in the standing domain, because it implies that we didn't find enclosed holes in structures. So, well, using the typical, regarding the problem formulation, using the typical complaint formulation, one expects that some holes appear in the final layout because we know they increase stiffness. But yeah, by including an outside void frame of few elements and incorporating the connectivity constraint, is expected that these internal holes try to connect to the boundary through the outside void frame to obtain a structure connected in both phases. Here, the connectivity constraint is implemented in the following way. We use a lower bound lambda2 min that varies in a continuous way using a typical continuation strategy between 1.05 1.15, and we also decide to normalize the constraints to 1 because we think that is more stable. And actually, this is what motivates us to use the shifting I mentioned before. And also, we have used a density filtering and a projection after having convergence. Well, the first example is the typical cantilever beam with a load in the middle point of the right edge. For this mesh size, the structure is connected in both solid and void phases. So if we apply the connectivity constraint, we obtain the same. But when changing the aspect ratio, obviously optimized designs with and without connectivity constraints are different. With connectivity constraints, of course, are connected, but obviously are worse in terms of compliance. And the same if we use another aspect ratio. And the same conclusions can be derived from this 3D example. This is also a very benchmark problem. Here we have a 3D cantilever beam, which is clamped here, and we are applying here a torque. And we know that for an enough volume fraction, optimal design corresponds to a thin wall cantilever with a very big hole inside. And when applying connectivity constraints, the optimal designs corresponds to a truss-like structure like the picture on the right. So in that way, the hole inside tries to connect to the outside, to the boundary. Okay. So yeah, to finish with, I would like to mention some work in progress. Yeah, we know that yeah, in this case, these two connected graphs, we know after seeing the presentation that this make the Laplacian matrix has two null eigenvalues. In that case, we haven't applied shifting. So we have two connected graphs, and this means that we have the first eigenvalue and the second eigenvalues are 0, but not the third one. Well, okay, but we also know that there is a direct correspondence between two connected graphs and two connected continuous domains. So if we solve that, which is called here the Newman Laplacian problem that corresponds with this PDA in omega, where omega is these two subdomains, the first and the second eigenvalues are also 0, but not the third one. So somehow there is a kind of relation between the continuous problem and the other discrete problem. So now we are working in developing a mathematical model that, based on the Newman-Laplacian problem, trying to explain connectivity from a continuous framework. And we have obtained some preliminary results that are really promising, actually. That's all so far. Thank you for paying attention.
Thank you very much. And in the chatting room, we already have the 3 questions, long questions. So I think the Alberto can type their answers in the chatting room, and when other people are there presenting. So is there any question regarding the presentations? Is anybody? I think it's really a good idea to analyze the distribution of design variable using the graph and to impose the constraint. So Alberto, we have the 3 questions in the chatting room, and can you answer some provide comment in the chatting room?
Can I have a quick question?
Yeah.
A small question. Thanks for the talk. So I understand this is a kind of a way to control the topology, right? If you don't allow any enclosed voids, it means you have a certain topology of the design. Could you also, by controlling the eigenvalues, make sure that you have exactly one enclosed void in the design?
So, but what's the question? Sorry, what's the question?
So by changing constraints through the eigenvalues of this Laplacian matrix, could you also make sure that instead of 0 enclosed voids, you have exactly one enclosed voids, but not 2 enclosed voids, for example?
You mean if you want to control the number of inclusions?
Yes.
Yeah, we haven't done it yet, but it's possible to do.
Okay, that's very interesting.
You have to control, yeah.
Kind of topology control. Yeah.
Yeah.
Oh, yeah. So I think we should move to the next presentation, and please, Albert, to give the answers in the chatting room during the other people, the presentations.
Thank you.
So next speaker is the Picelli from the Brazil. Picelli, can you share your presentation? Yes, go ahead. So the Dr. Picelli will present the topology optimization of the turbulent fluid flow via the TOBS method and geometric trimming procedures.
Yeah, thank you, Professor Yoon. Thank you, Professor Yoon. Do you hear me well?
Yes.
Hello? Ah, okay, cool. Yes, thank you again. My name is Renato Picelli. I'm an assistant professor at the Polytechnic School of the University of São Paulo, and I also work for the Research Center for Greenhouse Gas Innovation. I would like to thank all my co-authors who contributed to this work with me. I will start with some introduction, motivation. I'll give you my main objective. I will skip literature review due to time constraint, and I will talk about the key idea of my presentation today, which is turbulent flow and the TOBS GT method, ending up with numerical results and conclusions. Yeah, most of you might know that topology optimization of fluid flow became one of the main topics in the field. It's a trending topic. Let's say we have here a square domain. We want to design a fluid flow path in it. Let's say we have an inlet velocity in here, and we have an outlet velocity in here. We want to design a fluid flow path. This is a pipe band example. We want to design a fluid flow path which requires less energy to a fluid flow to be pumped. So this idea is reflected in the fluid should be defined as variable 1, and solid is defined as a variable 0. So this idea is reflected as minimizing fluid energy dissipation, subject to a volume fraction constraint. Well, this was fine until when Borval and Peterson began the topic, the fluid flow topic. This was fine until a few years ago is that we were designing only laminar flow, but challenges now begin when fluid velocities are increased. And then we go to high Reynolds flow. High Reynolds flow imply that we have a turbulent flow. You can see here an illustration that goes from, that explains or that illustrates laminar flow transitioning to turbulent. You can see here how more complex turbulent flow is. And when we're doing, when modeling turbulent, we require caution in the computational modeling of it, either by using refined meshes or turbulence models. And that specifically requires the information at the fluid walls. So the information at the fluid walls is important, either to refine the meshes at the fluid wall or use a turbulence model like turbulence wall functions at the walls, etc. So when doing topology optimization with turbulent model, turbulent flow, we need the fluid flow wall information. So my main motivation starts with, until the time we did this work, there were only density-based methods or either continuous variables methods that employed laminar flow topology optimization. So the main issues with these methods start with, they do not offer explicit fluid flow walls. This is a result for a laminar flow optimization, the same pipe bend example here. I did this from console myself. Of course, if you're more experienced than me in density-based method, you would get maybe a better convergence, but I got the final solution that usually is obtained. And because we do not have the fluid flow walls here, we have a large presence of grayscale. We cannot apply, we cannot refine meshes or employ turbulence models at the wall. So we need the information at the wall, and we do not have here. The second issue is the dependence on material interpolation. This is not actually only my opinion, but literature also reports that these methods, they often demand exhaustive parameters tuning in order to go for a 0-1 final design. And this becomes more problematic for higher fluid velocities. Third issue is regards the fluid flowing inside the solid or leaking into the solid. Here, you can see that I got a nice solution with console, and I do not get any fluid flowing into the solid here. I do get a nice fluid flows flowing only in the fluid domain, but it's still for higher velocities that might easily happen. The fluid might even easily leak into the solid part, and we still are solving for the whole domain. As we're solving for the whole domain, we're increasing the computational cost, or at least we have to solve all these large unnecessary domain, and we're still solving for the pressure here, which actually should not exist. So computational cost might be an issue here, and also accuracy. So topology optimization of turbulent flow might be very challenging, or might be very hard to be done with fixed grid method. So this is one of my main motivation. We need to devise, I want to devise here with my co-authors, an explicit boundary method for turbulent flow topology optimization. The method I'm presenting today is based on a body-fitted approach, okay? And in either you could use Arts material or immersed boundary. So up to the point that we were doing that work, the paper by Joe and Casper, they reported that there was no other explicit boundary method developed for turbulent flow at that time, up to the point I understood. But nowadays there are three main methods, or there are three available methods published recently: level set, and our method today, which is TOBS GT, that uses a body-fitted approach. Another motivation that we had is that our group here in the past, or in the recent past, we developed the first method to do fluid flow topology optimization, is still in laminar flow, by using sequential integer linear programming, by using integer variables with formal mathematical programming, because with that we can get explicit boundaries, and the method also showed to be very less dependent on penalization. But the main point here is that we still get explicit boundaries, but we still get jagged boundaries, and that's not very good for turbulence either. We used the branch and bound and SIOP, and the solver was based on TOBS method that my colleague and myself developed in 2018. Okay, so my main objective here is to develop an explicit boundary method that tackles the three current issues with fluid flow topology optimization. and also offers an alternative to the level sets. As I said here, a level set, and we have another method. So we are using the Rand's equations, okay, to model turbulence here. We are using a linear interpolation model. We are still doing the inverse permeability approach, the standard inverse permeability approach, but using a linear model. As we are using integer variables, we don't need a more complex model than that. We are using the K epsilon turbulence model just for illustration. Okay, we solved 2 extra equations on turbulence variables. We have an inlet velocity boundary condition, an outlet pressure boundary condition, and we have turbulence boundary conditions here as well, turbulence on turbulence variables. We want to minimize the total fluid energy dissipation subject to volume constraints to test our example. So this is the example I said in slide 1. If you want to pump a fluid through a pipeline and you want to minimize energy, you want to require less energy to pump it. It usually goes for turbulence in our engineering systems, and this is the energy dissipation we are using with the inverse permeability term here as well, and the linear interpolation here. We are using a volume constraint and binary variables, just to be clear. So the main idea of the method is this one. This is the key method, the key idea of the method. So we have an optimization grid, a fixed optimization grid, which provides us a 0-1 solution with the TOBS. Okay, we identify and extract the contour of these solution. Again, like I said in the first slide, black is solid and white is fluid. We identify and the contour is smoothed, obtain a smooth contour, and is extract out of it, or remove out of it, or trim out of it the solid part. So that's why we're calling geometry trimming, the GT part of the TOBS GT method. So after defining or after obtaining a smooth CAD, we can generate either freely or you controlling it, like under CFD requirements, fluid dynamic requirements. We can generate a proper mesh for turbulent flow, or at least for CFD flow. We still have here the inlet. Let's say that's the pipe example case. We can model the walls with square elements to model boundary layers, and then we have a convergent CFD problem. We interpolate back to the fixed grid mesh, and then we carry out optimization again. So the idea is repetitive. Okay, of course, topology optimization is an iterative method. At every iteration, we have a 0-1 solution, and we do the trimming. So every iteration, we have a body fitted mesh with a smooth CAD that with proper refinement at the walls to model turbulence, and then we compute sensitivities and we interpolate back. Please be aware here, just to mention, we are using sensitivity filtering, and then we iterate until convergence. So we are using TOBS, the 0-1 solution that we recently developed, plus geometry trimming. So we have CAD geometries and free or controlled meshing. An important step is that we are using automatic differentiation. I am using Console Multiphysics, but you could use any other software that provides you that information. And then we have a 0-1 solution with smooth boundaries. Then we can include turbulence wall functions. So the first example I want to show is a laminar flow, actually. It's just so Reynolds number 300 is just to show the investigation of the geometry trimming approach, okay? So this is an U-bend example. We have an inlet velocity in here. We have an outlet pressure in here. So the fluid should go around this inner region that should be kept fixed as a solid. We are using here, we are comparing the geometry trimming approach with the standard inverse permeability approach. So this is solid model with the inverse permeability. And this is, the blue is actually obviously fluid. These are the properties. This is the initial gas design. You can see here for the kappa max, the inverse permeability value. For a very low kappa max, for a very low inverse permeability, we have fluid leaking into the solid here like this. And that's not what we want, right? We increase the inverse permeability to emulate better the solid, and to the point that there's no more fluid leaking into the solid. So this is this penalization is case dependent, okay? And when solving this problem with geometry trimming, we see that the geometry trimming solution tends to look like the solution with the high inverse permeability. However, without penalization dependency, because when the variable is 1, so you have a fluid, this term vanishes and your physics is not altered. But when your variable is 0, you have a solid. You also don't have this term because your solid is streamed out. Okay. Okay, so the pipe bend example again, but now turbulent flow. We have here an intervelocity. We are using a Reynolds number up to 5,000 here in this point. We have a fixed optimization point, and here you see the solutions, how the geometry trimming or the TOBS approach evolves. So start with a full fluid design. You don't need to start with a full fluid design if you don't want, but this example does. And then you see in 129 iterations how it evolved. Here, the key method again, or the key idea illustrated again. For the final pipe bend solution, you see the optimization grid in 0, 1. Remember, the optimization grid is kept fixed. So you have a 0, 1 black and white solution. And then we extract a smooth CAD. This can be done, to extract the smooth CAD can be done in different ways. We are experimenting with different methods nowadays, okay, after we publish this work. And you see here the nice CFD mesh. We have a modeling the boundary layers, etc., and the final solution. To end up my talk today, this is the last example. We developed a 3D pipe junction using turbulent flow. We have 2 inlets here. Yes, and we have an outlet here. We start with this initial gas design. We first solved for laminar flow, for very low Reynolds flow. We got this solution. And we turned on the turbulence and K epsilon turbulence model to increase the velocity to a Reynolds number of 5,000. We got this final solution here. Another important point to mention is that our optimization grid is fixed, as I said, and because of that, we have a large number of optimization points. However, when you do the trimming, either with this method or either with the level set with the body fitted approach, you can model only what matters, which is actually the fluid, right? And modeling with what matters and modeling it properly with a CFD mesh, you can use much less points than your optimization points. And then because of that, you can solve the problem in a cheaper way. So this might be a relatively cheap method for a complex problem. So concluding, geometry trimming approach, the GT approach was combined with the 0-1 method we developed previously. So we call it TOBS GT. We have then explicit and smooth fluid flow walls. Penalization continuation schemes are not necessary, and penalization is much less dependent in this case. We could discuss, I'm happy to discuss this point because this might be new in the community. Solid regions are trimmed out, so we don't have even any chance to have fluid leaking into the solid, and topology optimization with fluid flow, turbulent fluid flow was solved. Thank you very much for the research foundations we have here. They are helping me a lot, and thank you all for listening. It's an honor to be here in this community.
Yeah, thank you very much. And so the presentation is open for the discussion. Is there anybody who had some questions? Oh, there is one question in the chatting room.
In the chat, okay.
Yes, it's about the computation cost about the remeshing operation.
Oh, good. I have backup slides. Let me see if I have those.
Mm-hmm.
Oh, yeah, I have it here. So computational cost keeps being the FEA solver. You see here, the computational cost of the FEA solver is much larger than any of the other steps. Okay. This is the graph without the FEA solver in the right here. You see, mesh generation, of course, is taking a bit of time, especially in the beginning in these solutions. But later on, wall smoothing is taking longer. Thanks for the question.
Mm-hmm. So very interesting questions, and thanks. Yeah. So
is that all?
I think there is one question from the Casper.
Okay, so I see the question here.
Yeah.
Yeah, so, yeah, that's a good question. Why not to use? Am I attached to 0-1 solution? No, not exactly. I could actually. I thought about it. You guys gave me that suggestion when I visited you. I thought about it, but we want to keep in the digital approach. Let's see. We want to keep turning on and turning off pixels. So because of that, we have the ability to create holes, and we are closer to SIMP or density based in the way material distribution was first developed for topology optimization. We do not want to use a parametric level set in terms of in the optimization. We are now using actually a parametric level set only to smooth the CAD. Okay, in the paper we published, we use the image filtering smoothing. Nowadays we are using level sets to model the smooth CAD, but we still want to keep the binary solution because that gives us less dependency on penalization.
Okay.
Thanks.
Thanks. Yeah. Thank you, Picelli. So let's say thanks to the Picelli again.
Thank you. Thank you, everyone. Bye.
So the next speaker is about Stijn Koppen.
Yes, thank you very much, Professor Gilho Yoon.
Yeah.
First of all, for the invitation. I'll start my screen. Yes, and I will explain you today about the study I did together with Matthijs Langelaar and Fred van Keulen, which is titled Efficient Multi-Partition Topology Optimization. And it's all about reducing the computational cost of solving problems with multiple load cases without making approximations. And to explain this, I will introduce a minimum working example, which you can see here on the left. So we have a domain that is fixed on two sides, and we have a design that is represented by the array of design variables X and a state U. And we have 2 points of interest, point A and B. And at point A, there's a force, which in this case is applied with value 1. And in the context of gradient-based topology optimization, which we solve in a nested analysis and design setting, we try to solve this problem and analyze the computational costs. Now we consider here that we have a response function, G, that is a function of the state at point B. And in such a setting, where we also consider linear or linearized physics, we typically have to solve a system like this, K use F. And we do so by partitioning this system into free and prescribed degrees of freedom. So in this case, obviously here at the boundary conditions, is the state is prescribed, and in the middle, the state is free. And we can see that for such a type of problem, this is the resulting system of equations that we have to solve. And we can do so using direct methods or iterative methods. And for the explanation of this, in this talk, we just assume we use a direct method, but the same conclusion holds for iterative methods. And then the dominant cost in every design iteration then is solving this system of equations. And in this case, that cost will be a single factorization of this system matrix, and in this case, 2 right-hand sides. So the cost associated to that is the back substitutions that are first of all related to the forward load, and then the second one to the adjoint load. Now this cost may obviously be expressed in terms of time or also in the number of operations. Now, should be mentioned, this is a single partition optimization problem, but if many real-world problems, we're dealing with multiple load cases and also response functions that depend on the state of multiple load cases. So that is our interest. And we're first going to show the computational cost associated if we just use a let's say, naive approach. And we have the first load case that is the same as previously shown. And we add a second loading condition where we made one very important change. Instead of having here load 1, we now have a displacement, or we prescribe the state to 1. So we have there a change of boundary condition. And we assume that we have a response function that depends on the state in point B, and that depends on that for both loading conditions. Now, as a result, we have to solve this system of equations. And in order to obtain this result, we have to do 2 different partitions because the boundary conditions are changed. Yeah, so in this case, the partition of associated to load case 1 and the partition associated to load case 2 are not similar. As a result of that, the computational cost will increase. In this case, we have to perform 2 factorizations and a total of 4 right-hand sides, 2 associated to the forward analysis and 2 more associated to the adjoint analysis. Now, our target is to see if we can reduce this computational cost without making approximations. And that is what we call the condensation approach. That is what is presented in the paper. We consider the same loading conditions and response functions for this minimum working example. And we're going to solve this in a couple of steps. And the first step is to identify the so-called primary degrees of freedom. And in this method, we define the primary degrees of freedom as all the degrees of freedom that, first of all, are relevant in the response functions. So that is the degree of freedom related to point B in this case. And the second one is all the degrees of freedom that change between known state and unknown state in the different loading conditions. So in this case, that's going to be the degree of freedom at point A. So green is going to be our primary degrees of freedom, and orange, that is all the resulting degrees of freedom, are going to be the secondary degrees of freedom. Now, what we propose is to build a reduced order model, but an exact reduced order model using static condensation. That is what is shown in this equation. And the largest contributor to the computational effort is going to be solving this system of equations. That is, in fact, a single factorization that is required here. And the number of right-hand sides is 2, equal to the number of degrees of freedom in the set of primary degrees of freedom. Now, with this reduced order model, which in fact, in this case, is only of size 2 by 2, we can continue the analysis and we can basically apply the naive approach now on this reduced order model. So basically what we did here, these set of equations that are very expensive, we now do that on the reduced order model. And therefore, because this reduced order model is very small, this is basically free of cost. Now, obviously, we also need to retain the state. So that is the state of the secondary degrees of freedom. And we also have to get the adjoint state. And what we see, if we try to obtain that we have to solve another system of equations. So that might become very expensive. But surprisingly or not, we have already solved this system of equations. So we don't need to redo that. And that makes basically this model or this method quite efficient, because in total we saved now 50% of the computational effort compared to a naive approach. Obviously, there are some specifications what your problem has to satisfy in order to get this type of gain. With this, let me show you a couple of variations. So we have here the 2 load cases, the naive approach and the condensation approach. And we see for a typical problem, if we have an applied load here at point A, and for the second load case, we have an applied load at B, that those 2 have the same partition. And therefore, the gain that you can achieve is relatively small. But if we change the boundary condition from prescribed to non-prescribed, we see that we get approximately 50% gain by applying this method. In the same case, if we do in both cases have an applied load, but we modify the stiffness matrix, for example, by adding stiffness, for example, from an external piece that we're interested in, that would also require 2 factorizations. And if we apply the condensation approach, it's only a single factorization. So again, approximately a gain of 50%. Now, how does this translate to bigger problems? I will explain this thermal conductivity problem, where we have distributed in the domain 100 points where we're interested in, and we consider 100 different loading conditions. For each loading condition, we have one of the points is a heat sink, so that is prescribed state, and there's a load of random magnitude on all the other points. This means if you would solve this in a naive approach, you require 100 different partitions, and therefore 100 factorizations, as well as 100 or 200 right-hand sides, depending whether you take into account the fact that the adjoint loads are linearly dependent on the forward loads. Now, if you apply condensation, so you first make a reduced order model of all these 100 points, that will cost you 1 factorization and 100 right-hand sides. But then if you have the reduced order model, the rest is basically for free. So you can expect for such type of problem a gain of 100. Now let me wrap up because of the limited time. What we conclude in this work is that the method that we developed is able to reduce the number of factorizations and the number of right-hand sides without making approximations of the accuracy of solving the problem. And this is especially applicable to problems with multiple close to similar partitions. So for example, when there's only a couple of degrees of freedom which switch between known and unknown. And at the same time, when we have responses that depend on a very small set of degrees of freedom of interest. A typical application of this would be compliant mechanism design. Yeah, thank you very much. Looking forward to questions and discussion.
Yeah, thank you. And is there any questions or comment? So I have one question. So in the last example about thermal conductivity, do you have can you provide a more explanation about your applications?
Actually, not so much. You could say because this is let's say a special case that we developed to show the how it scales basically. But you could say when you have a problem and you want to have a good connectivity between different points, but you're unaware which one is going to be the sink and which one is going to be the heat load. So when you have uncertainty in your problem description, so it's basically a worst case scenario that you now model for.
Because this complex geometry is really interesting, and so I would ask. I want to ask whether there is some specific application or not. So,
no, not really.
Yeah. Please comment. Any other questions? If not, let's thanks to Stijn Koppen, and let's move to the next speaker.
Thank you.
Thank you. The next speaker is Hao Li from the Kyoto University, Japan. The title is about the fluid problem in considering the natural convections.
Yes, Professor Yoon, can you hear me well? May I start?
We can see your presentations.
Yes.
Okay, thank you. So thank you, Professor Yoon, for your kind introduction and your invitation. And good evening, good morning, and good afternoon, everyone. It's my great pleasure to present a talk webinar to all of you about our recent works. My name is Hao Li at Kyoto University, and I'm working in Professor Nishiwaki's group as a postdoc. So the topic here is about optimum design the thermal modeling for 2- and 3-dimensional natural convection problems. Okay, let us start with a general introduction. So the passive heat sinks relying on buoyancy to drive surrounding air motion does not require a pump or a fan to drive flow. And therefore, it is a good candidate for those low noise and compact electronic devices, such as telecommunication devices, LED lamps, and semiconductors. So in the state-of-the-art work on topology optimization, we here notice 2 representative works. The left one was done by Professor Joe Alexanderson in 2016, and they used a high fidelity modeling, which means that the full Navier-Stokes equations are strongly coupled to the convection diffusion equation through the linear Busnitz approximation. And this was actually the very first work to present the large-scale 3-dimensional passive heat sink design using TO technique. And later on, Dr. Pollini proposed an optimization sequence using the high fidelity model at the beginning stage to evolve the topological configuration in the correct direction, and then switch to a low fidelity model, and more specifically, it is the Pullman's approach, to accelerate the optimization process. So those 2 works pioneered ideas, and they are really impressive. But to achieve such a high resolution design, it seems that we have to use a large machine, which is not always available to the general user. So it remains us an open question that how can we get a 3-dimensional design using a high fidelity modeling, but at a reasonable computational cost? Although it looks like a simple technical issue, but it is indeed quite difficult to find an efficient algorithm in practice. And that is the key motivation of our work. So hereinafter, we provide you which key ingredients we have used in our work and which are new to the best of our knowledge. The cornerstone here is the reaction diffusion equation-driven topology optimization methods, where a heaviside projection is applied together with the interpolation of material properties, which is also called the LSAT material approach. Then the implicit level set function is evolved by solving the reaction diffusion equation based on the topological derivative. But here we also note that in practice, we can also use density-based sensitivity as the reaction source term, because it tells the gradient-based optimizer the descent direction as well. Okay, to deal with the inequality constraint problems, we use the augmented Lagrange methods, and the Lagrange multiplier is updated as in equation 5. Next, as we briefly discussed above, we hope to solve not only 2-dimensional problem, but also large-scale 3-dimensional problem. And in 3D problem, the most time-consuming part in this workflow lies in the solution of the sequence of linear systems. So here we use an open source FEA software, FreeFEM, and this parallel framework, MacroDDM, which provides multiple high-level FreeFEM macros that one can call in a script at different steps. For example, for distributing a mesh, for performing parallel finite element interpolation, or to export solutions in a distributed fashion. And we thanks to the great efforts by our French colleagues, Professor Pierre Jolivet, for the PETSI interface in FreeFEM. The final key ingredients in this workflow is the local mesh refinement. In the present work, we choose to use the body-fitted mesh revolution algorithm proposed by Professor Alia and his colleagues. So the body-fitted mesh is a kind of surface capturing technique, allowing us to disjoint and reunion subdomains. So, and this technique is essentially needed in the fluid structure interaction problem. But we also note that for many other fluid-driven TO problems, at least for laminar flow, such technique is not necessarily needed. And if we can use very fine mesh around the fluid-solid interface, then it is not a too big issue. Okay, so let's move to the optimization formulation. Let us consider a cavity here in which we have a heat source in red. The blue domain is the solid region, which is the heat sink design space. The surrounding air is the coolants. We intend to design a compact heat sink structure that can facilitate the natural convection around the heat sink. The governing equation here is the Navier-Stokes, which is strongly coupled with the energy equation through Boussinesq approximation. And then we use the ramp scheme for the material interpolation, for the thermal conductivity kappa and the inverse permeability alpha. And we use the continuous adjoint method for deriving the sensitivity as follows, where the adjoint velocity, temperature, and the pressure can be solved as in equation 12 and 13. So here we show several interesting numerical investigation cases. At the first place, we benchmark our solver against the experimental results in the literature, and we can observe a quite good agreement between experiment and numerical analysis. And next, we examine the transient fluid flow behavior. To do this, we use a second-order finite difference scheme and construct the Newton sequence and solve equation 6 iteratively. And here we have an animation to show you. So in this simulation, the gross Hopf number is relatively high, which means that the heat transportation is dominated by the convective effect. And it cannot converge to a steady state, as you see. But hereinafter, in optimization problem, we first make sure that the problem can converge to a steady state, and then we can make the steady state assumption. Okay, finally, let's see optimization test case. So we also have a animation for you. In this case, we run the optimization algorithm for 300 iterations on a standard workstation with only 32 ampere processes. And the total runtime is about 41 hours. For the last iteration, the linearized fluid system has around 3.56 million degrees of freedoms. We also present a complete product development cycle from topology optimization to B-spline conversion to the performance validation and finally to the prototype. Okay, next we would like to show you some extensions. The first is the anisotropic meshes, so which can fit high aspect ratio elements along the regions of rapid variation of the solution. So they are preferred for situations like boundary layers observed in the fluid mechanics problem. And again, thanks to our French colleagues devoted to the development of the parallel MMG, which is a parallel version of MMG, so that we are able to output a very large mesh with multi-million tetrahedron elements in a distributed way. And please take a look at our recent brief notes on SMO. The second extension is about high resolution and feature-rich design. We impose a local volume constraints realized by a PDE filter together with the distributed mesh adaptation. And then we can reach the lattice design shown in figure using a desktop within 8 hours. And also we can extend this idea to the thermal fluid problem as well, so that we can reach such a bifurcated branch-like structures as shown in these slides. Last but not least, many of the key ingredients here can be also used in other popular TO techniques, such as density-based approach. As we show here, which is a thermal fluid benchmark problem. The key idea is we have an adaptive mesh for physics computing, but a fixed fine mesh for the design using MMA. So we believe that these extensions can make our research works more value added to our community. Okay, let's conclude with a short summary. In today's talk, we present you an easy to use and highly scalable TO framework implemented in FreeBEM, PETSI, MMG, parallel MMG to solve the linear or nonlinear problems in 2D and 3D settings. That's the end of my talk. Thank you so much for your kind attention.
So thank you. Very nice walk. So the presentation is open for the discussion to the ground. Any questions or comment? If there is no question or comment, let's thanks to the Hao Li, Dr. Liu again.
Thank you.
Yeah, thank you. The next presentation is from the Professor Ikjin Lee from Korea.
Okay, so can you guys see my monitor?
Yeah.
Okay, thank you for introduction. And thank you for inviting me to this topology optimization webinar, even if my research topic here is not directly related to topology optimization. So I'm going to talk about the reanalysis-based multi-fidelity RBMF surrogate framework for efficient structural optimization, which was published Computers and Structures a couple weeks ago. And my name is Ikjin Lee, and I'm associate professor at KAIST Mechanical Engineering Department. So these are the contents for today's talk. And let's move to the fundamentals of the proposed study. So let's review surrogate model. So the definition of surrogate model, or also called meta model, is a mathematical model that approximates the performance of the real engineering system. So when expensive simulations are iteratively required, such as in design optimization, which we usually use, then since the computation cost for one simulation is highly expensive, then it is not efficient to use this simulation for design optimization. So instead, we could use a surrogate model or a meta model, which approximates the computer simulation model. So to generate this surrogate model or meta model, we use a limited number of samples, and then using appropriate surrogate modeling method, we could build this approximation model. Once accurate surrogate model is generated, then we could use this surrogate model to perform a design optimization. And let's briefly review a multi-fidelity surrogate model. So the previous surrogate model explanation uses a single fidelity or single data source to generate a surrogate model. If there exists multiple fidelity data, then we could generate this surrogate model using these multi-fidelity data sources. So the definition of this multi-fidelity surrogate model is an efficient surrogate modeling method combining high fidelity data and low fidelity data. And if experiment is available, then this experiment could be treated as high fidelity data, and the simulation could be treated as low fidelity data. And for the simulation, if we use fine meshes, then that simulation could be treated as high fidelity, and the coarse mesh could be treated as low fidelity. And the 3D model can be treated as high fidelity, and the 2D model can be treated as low fidelity. So usually, high fidelity data are computationally expensive and treated as accurate result. And low fidelity is computationally cheap, but accuracy is also relatively poor compared with high fidelity data. So by just using high fidelity data in this figure, so which is actually for high fidelity data only, then we could build this blue dotted line as a surrogate model, which is different from red solid line, which is treated as exact result. But instead of using this high fidelity data only, if we include more low fidelity data, then we could build this black dashed line as a surrogate model, which is more accurate than single high fidelity surrogate model. then if we can build this accurate surrogate model, then we could use this for design optimization. And let's briefly review a structural reanalysis method. So definition of this reanalysis method is efficient approximate solution of modified design with help of the initial design. So here, first we need to solve this matrix equation using finite element analysis at a given design. Then we could obtain the solution of this matrix equation, which is actually at the modified design without solving a full finite element analysis. Instead, we could use reanalysis method. So for example, for this structure, the given design is 1.8 millimeter and also 1.8 millimeter. And to obtain the displacement of this structure, we need to solve a full finite element analysis. But for the modified design here, so now thickness of part 1 is 2.0 and thickness of part 2 is 1.4. Then since we have solution here, then we don't need to solve full matrix equation. Instead, we could use the reanalysis method. Yes, so here from this table, we could see a reanalysis solution can be obtained with 1/3 computation cost, and error is very small. So research overview of the paper is here we're going to build a reanalysis-based multi-fidelity surrogate framework to generate accurate surrogate model. So which means we will use high fidelity data and low fidelity data. And also we will use exact result and also reanalysis result to build the surrogate model. So this slide shows 4 types of data. So there are high fidelity samples and low fidelity samples. And in each high fidelity and low fidelity data, we could have high fidelity exact sample, HFE, and also high fidelity reanalysis sample. Also a low fidelity exact sample and low fidelity reanalysis sample. So by combining all these samples, we could build accurate surrogate model with less computational cost. And for that, we need to propose sub-strategies. So first one is called the reanalysis sample classification method. So first, we are going to generate this kind of samples using Latin hypercube sampling or any other DOE method. Then if we can simulate, if we need 4 exact samples, then these samples are classified into 4 subregions. And the center of each cluster can be treated as exact samples. So we have 4 exact samples and 4 clusters, and other samples are obtained using reanalysis samples. But if the reanalysis solution diverges, then that sample is converted to the exact sample. So if there is no divergence, then we need 4 exact samples and a remaining reanalysis sample. But if one reanalysis solution is diverging, then we need to convert 1 reanalysis sample to exact sample. And even with 4 exact samples and the remaining reanalysis sample, the generated surrogate model may not be accurate. Then we need to include more samples to obtain accurate surrogate model. So that is done by reanalysis sample or infilling method. For that purpose, we need to introduce acquisition function, and to the point that maximizes acquisition function is the next infilling point. So here, this diamond is next infilling sample, and we need to include 1 more sample here. And then to obtain the solution here, first we need to find closest exact sample. So in this example, T4 is the closest exact sample. Then using this D4, we could first find the reanalysis solution. And if it diverges, then this must be treated as exact sample. So this flowchart summarizes the proposed RBMF framework. So we need to generate initial low fidelity and high fidelity samples and divide these low fidelity or high fidelity samples into exact and reanalysis samples, and obtain responses from exact or reanalysis and high fidelity or low fidelity samples, and then build RBMF surrogate model 1 or 2. And if this generated surrogate model is accurate, then we will use that surrogate model for design optimization. And if it is not accurate, then we need to put more samples until accuracy criterion is satisfied. And let's see one optimization example. So here, electric multiple unit EMU is used for the example. So we are gonna optimize this car body where 5 design variables are used. So thickness of each frame is a design variable. For this, we're gonna use a high fidelity model and a low fidelity model, and degree of freedoms are different like this. And the computational cost for high fidelity exact sample is 193 seconds, whereas low fidelity exact sample requires only 2.8 seconds. And for reanalysis, high fidelity reanalysis sample requires 63 seconds, and low fidelity reanalysis sample requires 2.1 seconds. So here we can see if the model has more degree of freedom, then reanalysis effect is much larger. And optimization formulation is given here. So we are going to find the 5 design variables to minimize mass of the car body subject to displacement constraint and stress constraint. And the first table shows accuracy comparison. So here, first 3 row means Kriging 50, Kriging 20, Kriging 15 means a single fidelity surrogate model by just using high fidelity exact samples only. And HK15 is conventional multi-fidelity surrogate modeling, which uses 15 high fidelity exact sample and 100 low fidelity exact samples. And this column shows the equivalent number of high fidelity exact samples. And RBMF1 is proposed multi-fidelity method, which uses 3 high fidelity exact samples and 12 high fidelity reanalysis sample. But in this RBMF1, we don't use a low fidelity reanalysis sample. And RBMF2, we will use low fidelity reanalysis sample as well. And RBMF2-2 has 5 more samples included using sequential sampling. And here in the last column, we can see by just using 1/5 of this equivalent high fidelity exact samples, we could obtain almost a similar accuracy by using the proposed RBMF. And from this table, we could also see the optimized result. And again, by using almost 1/5 of the computational costs, we could obtain almost the same optimum design by using Kriging 50 and this proposed RBMF2 method. So this is the conclusion. So in this paper, we propose RBMF surrogate modeling framework for efficient structural optimization. And to maximize the performances of the proposed method, we also propose 2 sub-strategies such as reanalysis sampling classification and the reanalysis sample infilling method. And the numerical result shows, verifies the proposed method is working very well. And in this paper, we just use a simple linear structural problem, but we are going to apply this proposed method to nonlinear vibration or dynamic problems as well in the near future. Thank you.
Yeah, yes, thank you. So this paper is open for the discussion to the floor. Is any questions or comment? I have one question. Nowadays, as you know, the neural network or AI has been widely used for the regression model. So do you have any plan to apply the AI or deep learning for this kind of work, RBDO?
Yeah, actually, I'm working with my students for a multi-fidelity method using a neural network. So for big data problem, so neural network is much more efficient than Gaussian process or Kriging, which was used in this presentation. So actually now I'm working on that as well.
So our goal also the working for the autoencoder model to reduce the system of size, like the static condensation or the model of the reduction scheme. So I'm very interested about the how it can be expanded to this kind of research.
Okay, thank you.
Okay, thank you for all speakers and the attendees. So I think that we should this is the end of the webinar. So thank you all of them to join this webinar, and also the other student and the papers. So there are still ongoing discussion on the chatting room. So if you want to join, you can remain or you can leave now.
Yes, thank you for joining us today, and Gilho, thank you for organizing the session today.
Thank you.
This is the last session before the new year, so many people will go for holiday. So I wish all of you a nice holiday season. And the next session will be organized on, it is scheduled for January 26. It is organized by Professor Kat Malter from University of Colorado Boulder. So I hope to see many of you in January as well.
Okay, so thank you.